That P is really F.
Yes. You just restart. Right. Okay, so this is basically the concept of shear stress and normal stress. All right. Okay, now what about this one? Okay, so back to this example. Okay, when you apply a force here, 50. Okay, this one going to generate stress, right? Okay, what's the stress in this bar? How do you determine?
And you have to figure out the area.
You got to figure out the area. What's the area here, right? Okay, so let me just redraw it here. So somehow I can make a 3D drawing, a little bit nicer. You can see it. So this is the wall here. You're applying force P here, right? So the cross-section area, let's say this part is A. Now what's the stress? P over A, right? It's very straightforward. P over A.
So we don't have to worry about true or engineering until we get in a transient situation.
Okay. In this class, so far we not worry about it at all. Okay. The question was, when you stretch something, right? Let's imagine you stretch a rubber bar. Okay. When you stretch hard, the bar going to elongate, but the cross section going to shrink, right? So when you shrink, the area actually change. So then the question will be, you calculate the stress, divide the initial area or divide the final area, will be different, right? Okay, in this class, we always talk about only small, tiny deformations. So therefore, the area difference we'll ignore. Yeah, we don't talk about it. Later on, when you talk about these things for a large deformation, more advanced, we call continuum mechanics. Then there, this difference can be big. For example, if you have a piece of artery or you have a piece of muscle, right? When you stretch it, you can stretch twice long. So basically, the cross-sectional area can decrease by half. And then it's a huge difference. Then it's actually matter you use this final area or initial area, right? Okay, so here in this class, we're talking about the small deformation. So this one kind of limited. It's hard to use for soft tissue. When you study, heart or study arteries or any soft skin, soft tissues, right? But this is a starting point. So we'll just limit ourselves to small deformation. So we don't worry about the initial or the final. Another dimension is length. When you stretch a bar, you're going to elongate, right? So when we talk about the length, we don't try to distinguish how much the initial length versus the final length, because we think that deformation small, tiny. Right? So we treat that. Okay, so now that brings into deformation we just mentioned. Okay, now how you describe a deformation? Okay, you pull on this bar, right? You stretch it, it elongates a little bit. Right? So the length will change. Okay, now if I'm just stretch one, let's imagine I have a spring. So if I stretch this spring, okay, let me draw it here. Okay, say if I have a spring here, if I apply force, let's say P equals 10. Okay, this is going to move a little bit to here, right? Stretch a little bit. Now, what if we stretch a longer spring, this long, and I apply the same force P equals 10? How much is it going to elongate? Well, these two elongate the same amount. That's the question. Which one elongates more? This one spring is long.
They're the same diameter.
The same spring, I just have one longer than the other one.
That one should give you a longer.
This one will deform more, right? So it's the same thing. When you apply a load to an object, that object is going to deform. But that deformation will depend on the dimension of the object itself, right? It's like when you apply force, right? It will depend on how much area you apply this force to. You can have different effects. It's the same. When you have a large object, you generate a deformation, this much deformation. Or you have a small object, you want still generate the same deformation. These two are totally different. So we need something to describe the intensity of the deformation. Okay, what's that? Strain, right? So we're going to talk about the strain. Maybe I'll use a different one. Okay, strain. So what is strain? Actually, I already mentioned, right? So basically, it's the intensity of deformation. Right? Or you can say strain equal to the deformation divided by the length, initial length. That's a mathematical deformation, right? So it's equal to the deformation divided by the initial size or initial length. Right? But the word description will be the intensity of the deformation. Okay. Now, because we have two types of force you can apply to an object, right? You can apply a normal force, generate normal stress, or you can apply shear force, generate shear stress. Accordingly, you can have two types of deformation, right? You can have like this one, you stretch it, it will elongate. Or you can have this one, when you apply force, it will distort, right? Kind of rotate a little bit, right? So there's two types of deformation. Therefore, we define the two types of deformation. Okay, if you apply a force here, so this is the initial length, and then it deforms into somewhere here, this after deformation, so the force is applying here. Okay, so this one going to be an elongation. Let's use the letter delta. Okay, so we define the strain. Okay, so this will be the normal strain. Is this large enough or too small? Okay, all right. Oh, good eyesight. Okay, so the normal strain will be the delta deformation, right? Over the side. Which side? The length, L. Okay. Here it doesn't matter is it L0 or L. So L0 or L, it's the same because we talk about small deformation. Right? You have a 1 meter long bar. The deformation may be 1 millimeter or 1 micrometer. We talk about that level of difference. Okay, that's normal strain. Okay, what if you, like the other case, if you apply a force here, okay, you're applying force V here, so this thing will deform into this shape. Right? Now, how much this point, if you look at this point A here, how much this point move will depend on the size. Right? If you have a small block, you apply the force, it will move a little bit. If you have a huge, long block, it will move more. So basically, that depends on the size. So we need something define the intensity of this tilt, this turn. Right? Okay, what's the thing that doesn't depend on the dimension and give you the deformation that doesn't depend on the size and reflect how much it deforms? It's the angle, yes. So basically, this is the angle. So we call this angle gamma. And we use this angle gamma. So the shear strain, it's actually very simple. It's equal to the rotation angle gamma. Okay. So we use the angle to describe shear deformation, basically describe rotation kind of deformation. Okay, now what's the unit for this angle?
Which unit?
Not unit, dimensionless, right? How many radius? Or you can say, oftentimes we say 5 degrees or something, but basically it's not unit. Okay, what's the dimension for the normal strain?
Millimeters over millimeters, so it's not really, doesn't
It's
exist.
whatever meter over meter, then it's gone. Inch versus inch, it's gone. So basically not unit. So all the strains, they are now dimensional. Okay, so they are normalized intensity of the deformation, and there's no dimension. So basically, you have 1% deformation, 2% deformation, right? 1 degree deformation, 2 degree deformation. And basically, that's not unit. I say percent, that's not unit, right? So it's dimensionless, put it this way. All right. Okay. Any question about stress and strain?
The rotation of your angle gamma, I mean, how would I I just do that in radians?
Yeah, you can give in radius, or sometimes you can give translate into degree. Either one. Right? But basically, it's not dimensional. Right? Degree is not a dimension. All right. Any question about the stress strain and the internal force? That's a 3 new concept we could give you. So basically, chapter 1 is talk about lots of concepts. Right? So next time we'll talk about more concepts like linear material and also like a safety issue. Okay, but I think I want to maybe give one more example here. Right? We can do some calculation here. Any questions? No? You guys, no questions? Okay, let me give one example here. Okay, let's say I have a bar here, right? I know all the dimensions. So let's say the area A, I know it's equal to, we can just give a number. Let's say 2 millimeter square, right? Area has to be meter square. Okay, then we know the length, L equals to, give a number, let's say 2 meters, right? Applying a load, P equals to, give a value, let's say 4 newtons, all right? Okay, now can we calculate the stress in this bar?
200 pounds.
What's the stress?
Force.
What kind of stress you have in this bar? Normal stress. Okay, so normal stress, sigma, right? Equal to force P over area A. So that will be 4 Newton over 2 millimeters squared, right? Okay, what's the value? Will be 2 Newton over 2 millimeters squared.
200 pounds.
What if you translate to Pascal? So it will be 2 megapascal. Right? Because millimeter squared, that's 10 minus 6 meters squared. And then 10 6, that's what? That's mega, right? Megapascal. Okay. All right? So that's the. Okay, now, what if I feel the stress is too high? Maybe for steel, this is very low, very low. But for a piece of muscle, maybe this is too high. Right? How can I reduce the stress to support the same load? You can double the area, right? Any other way? You can control the stress. Basically, my question is how to control the stress, change the stress, reduce the stress.
Either increase the area or decrease the
You can increase the area, double it, right? Or
decrease the load.
decrease the load by half, right? So either double the area or half the load. Right? So basically, when you design things, you find, oh, I'm designing this thing, stress too high, so I can change it. Right? All right. Okay, now I want to go over another problem. That's basically the equation of equilibrium. Okay, so because we want to make sure everyone can get the equation of equilibrium correctly. Okay, so here's a cable, and I have another, let's say, a bar here, and this is like a joint connection here, and then I'm holding a weight, load W. Okay. Can we find out what's the stress in this one? Let's assume all the dimensions are known. All the A, area, and the lengths are all known. So this is a different example. Okay. So can we find out stress here and the stress here? So this W is known. Let's give a value, let's say 10. And this one, we know the angle. We can give a value, let's say 30 degrees. Right? Okay, how can we find the stress here and the stress here? Because we want to check if it's safe or not. You design this structure, holding a lamp there, is it too high?
Use 10 cosine 30 for the upper, and then just...
Okay, how to solve it? I'm not asking for the answer. How to solve it? How to find the stress here and find the stress here?
Free body diagrams.
You're going to need to find out what's the force here. right? Because you want stress, you need to find the force here. Find the force here. How do you get the force there? Equation of equilibrium. See, this is the problem from solid, but you need the equation of equilibrium. Okay, so to get the equation of equilibrium, what do you need? You need a first free body diagram, right? Okay, how to draw the free body diagram? You need to look at what are you looking for. You look in the force here, right? So you need to draw a free body that this force and this force shows up in your free body diagram. Then you can write the equation about it. Right? Okay, so with the free body diagram, you can just look at this point. So you can draw this part. So basically, we draw this part, this joint. You can use this joint as your free body. And then on this joint, you're going to have a load W here. What else? You're going to have force here, right? The force in this one. So this one.
10 per.
And the force you don't know, right? Let me make it this way, okay? To be able to calculate stress, you need to find out the force in the bar. And you need that force inside. So we can call it, you need to find out the internal force first, right? In the bars. How do you get the internal forces? You make a cut. So the easy way to say this one is, okay, let's make a cut here. Okay, once you make a cut, you can draw a free body of this part. So I draw a free body this part, so this joint. Okay, 30° here. The load is here. I made a cut. So this is the cross section I cut there. Okay, when you make a cut, then you're going to have a reaction, the internal force. So this one is the N we're looking for, right? What about here? You're going to have another force. Okay, so maybe we'll call this N1, this N2. Right? Okay, N1, N2. Can we find out N1, N2? Yeah, once I have this is the free body diagram. So I can write the equation of equilibrium. All right? So then, what's the equation of equilibrium?
Fx. Sum of forces in the x direction.
So sigma Fx equals 0. Right? Sigma Fy equals 0. Let's write sigma Fx equals 0 first. Sigma Fx equals 0. What do you have? You have negative N1, negative N2. That's this direction. And then you have the negative N1, but not in the x direction. So you have to have a projection. So that's cosine 30°. Okay, what else? No, W has 0 projection. So this one equals 0. So that's your first equation. Sigma Fx equals 0. Right? Now we need, this is not enough because I have 2 unknowns. I cannot find it. So I need another equation. I have sigma Fy equals 0. Sigma Fy equals 0. Right? All right, sigma y equals 0. Now write it.
W.
What else in the x direction? So you have a negative W, right? Plus
N1.
N1 has a projection in the y direction. So it should be N1 times sine 30° equals 0. Now, from this one, second one, can you find out N1?
Yes.
Okay, what's sine 30?
10 Newton, I guess. 10 whatever.
0.5, right? 0.5. That's an easy number to remember, sine 30°. Right? Okay, so this will basically say is W plus half N1 equals 0. So N1 equals twice W. Once you know N1, can you put it into this one, find out N2?
Yes.
Okay, now can you find out the sigma 1 and the sigma 2? Right? So the force N1 over A1. This one will equal to the force N2 over A2. Oh, sorry, I'm talking to myself. Okay, so basically you write sigma 1 will be N1 over A1. Sigma 2, A2, N2 over A2. Right? Okay, so I don't have any numbers. If you want to try it, you give some number, put it in there, you can finish it. All right? Okay, so we have more equilibrium problem. I give you a quiz, a prerequisite quiz. So basically, there are opportunity for you to practice the equation of equilibrium. Okay, try to do it by Friday. All right?